Okay, off we go. So here's the example we were talking about last time. Kind of a weird example. The big idea here is that the change of variables function ends up going backwards, which seems weird. And are you allowed to do that? And, well, yeah, you just have to adapt a few things appropriately. So the big trick that we saw was that the stretching factors are just reciprocals of each other. And again, now, don't fall for the notation. The notation makes it look like this is a statement about algebra of fractions. It is not. This is a statement about the algebra of determinants. Because even though we write these things as fractions, that's just notation. They are not fractions. So this is a non-trivial statement about determinants. So that said, here we are back again at this example. We have a pair of curves. Oh, come on. Well, close enough. Pair of curves like that. And we have this other pair of curves like this. The region that we are interested in is the thing that's kind of in between in there. Again, I know this looks like a really weird example, and what are the odds that this will ever come up? Well, in fact, it does. Now, this is a slightly streamlined, sanitization of the example I'm going to refer to, but there is a big example in thermodynamics. This is a huge example. It's very, very real. So that said, how would we compute an integral on this region? Right? This integral on that region right there. So the big idea, again, change of variables. Wouldn't it be nice if we could view this as being an image? Sadly, it's a little harder to do that. But what's really easy is to view something else as an image of it. Right? Going the other way. And I'll remind you what the big move on that is. The big move is step one. Write your equations as level sets, if you can. And here, they were given as level sets. Now, I'll point out they won't always be, right? They might be written with different algebra for whatever reason. But if you can get them in the form of level sets, then it's good to do so. And having done that, then look at the functions you're taking level sets of. Call them u and v. So that thing, I'm going to call u. This thing, I'm going to call v. Right? That's a pretty easy two-step process. And now it's all over but the celebration, pretty much. There's a little bit of algebra trickery we're going to have to pull. But basically, we have a change of variables function. At this point, we've got u and v as functions of x and y. Now, again, it's going kind of backwards, so that's disappointing and unsettling, perhaps, but we have a change of variables function, and furthermore, these curves look really nice, right? So these equations here for these curves here become just u equals 1 and u equals 2 because of the clever choice that we made there, thus giving us two straight lines. And then likewise, these equations for these curves become just, v equals 3 and v equals 4 because, again, of the clever choice that we made in setting this up, right? Choosing our change of variables function on the basis of, basically on the basis of what kinds of algebraic objects are most evidently participating in the algebra that we were given. And with all of that done, then you see that our new domain is just a rectangle. And we love rectangles. Okay. All right. Now we got to follow through with the algebra. We got to compute the stretching factor for this change of variables function. Keep in mind, stretching factors are the partials of the outputs with respect to the inputs. Again, weirdly, because of the fact that this is going backwards, u and v are now our outputs. It's just backwards. It is what it is. So we take the partials of u and v with respect to x and y, and a little algebra, and boom, there you go. There's your stretching factor. What you do have to keep track of is the fact, though, that this is the stretching factor going in the wrong direction. So we're going to have to figure out how to deal with that. Let me scroll down here real quick and point out where we're going to go with this. Reminder, this is the original integral we were asked to compute, and I want to point out specifically how this notation, this notational choice that I have here, will help me in this circumstance, and it'll help me keep track of, wait a minute, do I multiply, am I squishing, or am I stretching, or wait a second, but it's backwards, and very easy to get confused and turned around. The notation will keep track of all of that for you, and I advise you to let it. Right? It's super convenient. So how this helps us is we have to look at what we were given. We were given an integral dx dy. That's what I'm interested in computing. That's what I have. Well, then write down what in the, cringy, not technically reasonable, notational convenience would make a cancellation happen. And so what is the thing that I have to multiply by du dv to make this whole thing turn into the dx dy that I need it to be? Well, I need to apparently multiply by partial xy partial uv. Is everybody with me? You see how the notation did it for me? Right? The notation has kind of, I don't have to keep track of which way is it going and do I need to take a reciprocal. The notation tells me the thing that I need is partial xy partial uv. So that noted, I have computed, whoops, wrong color, I have computed partial uv partial xy. I need partial xy partial uv. I've computed the wrong thing, it seems. So, okay, no problem, easily adapted. The thing I want then is just the reciprocal of the thing that I have. Everybody on board? Everybody happy? Cool. And then we just kind of plug in. So 1 over xy squared, apparently, is the thing that I plug in for my the stretching factor that I need for this particular example, and multiplying all that times the integrand that I already had, of course, right? All together, my integral has turned into this. Now, it's tempting to say, all done, everything's been, we've computed our stretching factor, and we've got our new domain. Gotta love those rectangular domains. But you do see another problem here, probably, and that is, this is a UV integral, but my integrand's still written in terms of x's and y's. And why is this? Well, because I don't have a formula that I can plug in for x and a formula that I can plug in for y. That's what's one of the things that's really nice about having your change of variables function go what you might call the correct direction, the initial, our first direction, the primary, whatever you want to call it, direction, is that then you have a formula for x and a formula for y that you can just plug right in there, and the whole pullback thing, and again, everything gets rewritten in terms of u and v. We don't have that. I don't have a formula for x. I don't have a formula for y. So I can't just plug in, and thus I find myself with this problem of I'm apparently going to need to figure out a formula for x so I can plug it in there, and a formula for y so I can plug it into there. And here's the really good news. You technically don't. I don't need a formula for x or y. All I need is a formula for x to the 7th times y in this case. In other words, my eventual integrand. Right? I don't actually have to invert this function and literally solve for x and y. I just need to solve for my integrand. So now how do you do that? Well, this is going to be different in every question. Here's my integrand that I need to rewrite in terms of u and v. Here's u. Here's v. Now, so the problem I face then is I've got a product of powers of x and y, and I need to write that in terms of a product of powers of x and y and a product of powers of x and y. And so we now have to think to ourselves, what can I do? What kind of algebraic relationship would I expect between a product of powers of x and y and a product of powers of x and y and a product of powers of x and y? And so I speculate, because of the algebraic particulars here, I speculate that the one product of powers of x and y is a product of powers of these products of powers of x and y. I don't know. The algebra looks plausible, right? I mean, would you look at these things, the integrand and the u and the v, and suspect that, hey, maybe the green thing is I need to get some cotangents in here, right? I think cotangent of u and v or something. No, of course not. Right? So tailor your guess to the kinds of objects that you're dealing with. It's going to be different in every example. Right? This one, it just seems like if I have a product of powers and I want to get a different product of powers, maybe I should multiply and power them. It just seems likely. Okay. Now, having done that guess, multiply this all out. Notice that leads you to the very simple situation that I need a plus b to equal to 7. And apparently I also need to have a plus 2b equal to 1. In which case I win. And we find ourselves then just dealing with a little system of equations in Math 218. Solve however you like. There's my A, there's my B, and that tells me my relationships. And then, again, it's all over. And I have now rewritten my integrand. This then goes into there. And I literally then have a UV integral that I can just crank out. Everybody happy? All right. So that's, the one bit of bad news I'm going to say when your change of variables function goes the wrong way. Yeah, your algebra might have to get a little creative. Other than that, let the notation keep track of which stretching factor you want, and just follow the process. How are we doing? Is everybody with me? Everybody's happy? Okay. Alrighty. Moving along. All right, so we've gotten enough wins under our belt at this point. We've got several examples that we've successfully executed change of variables. I hope y'all see how change of variables in practice works. And so now let's worry a little bit more about some of the things that we kind of swept under the rug initially. And so in particular, where does this stretching factor formula come from? Let me remind you what the stretching factor is. We started with a little piece of the domain. Now I've drawn it much larger here than I did previously because I want to, study it in more careful detail. I know that its image is going to be a kind of a stretched out version of it. It might be stretched or rotated or something, right? But do keep in mind that these are very, very small things, right? And on small levels, functions are well understood by their linear approximations. And linear approximations there. The key word is linear. And so I should expect that the image should be very closely approximated by a linear variation on my initial rectangle. And so I'm going to say it's a approximately anyway. Close enough for our purposes. In the limit, the errors go away. Approximately a parallelogram. So I need to know what is the factor. What is the area factor between these two things? And try to figure out how much does the green rectangle get stretched out in its process of turning into the blue parallelogram. All right. So it turns out this is no big deal. I'm going to compute this blue area just directly. We have formulas for how to compute areas of parallelograms. Right? Chapter 1, old news. All I have to do is figure out what these edge vectors are. How am I going to find these edge vectors? Well, no problem, as it turns out. Those edge vectors, don't think of them as edges. Don't think of them as distances. Think of them as changes. Right? This vector here represents a change in the output of the function. Specifically, it's how much did the function change as my input changed by that. And this vector over here is really easy to understand. It's pointing exactly in the E1 direction, and its magnitude is du. Right? Keep in mind, this little subrectangle has a width du and height dv. So it's just literally E1 du. And how do I turn an input change into an output change? We turn input changes into output changes by multiplying times the derivative matrix. Again, chapter 2 fact, right? That's our fundamental perspective on what derivatives are. Derivatives are what you do to an input change to get an output change. I have an input change. I want the output change. So, boom. How we doing? Is everybody okay? Everybody so far? So, great. I have a formula then for this edge vector. This edge vector right here, the first column, in other words, of the matrix whose determinant gives me that blue area, the old chapter 1 formula for that blue area, is this right here. It's dg times E1 du. Thus, that. And then likewise, you can think through the analogous argument for that second edge vector, and it's this right here. So, boom. Everybody all right? Okay. All right. So, well, okay. Let's see here. Oh, I accidentally. Let's not forget. I'm computing this blue area right here, and now we're just going to play some linear algebra games. Don't forget, if you have a scalar factor in a column inside of a determinant, you can factor that right out. Right? Old rules about determinants. Right? Scalar factors in either rows or columns. You factor them out. And then likewise, this scalar factor dv in the second column factors right out. So that's nice. And then we're left looking at this matrix, and let's try to understand now, what can I say about this matrix? And there's a wonderful little simplification that happens here. That's a very special matrix, as it turns out. And I'm going to talk you through how to understand what this matrix is. Let's look at it one column at a time. Let's look at its first column. For example, what can I say about this first column? Ignore everything else. Just think just about this formula. dg times E1. I have a matrix times a standard basis vector. That rings a bell, right? That matrix times a standard basis vector is a column. The formula then, right? Multiplying a matrix times a standard basis vector. This is the first column of dg. Now, let's remind ourselves, why are we interested in computing dg times E1? Well, I'm computing it because it's the first column of the matrix I'm trying to understand. So, let's smash that together. The first column of the matrix I'm trying to understand is the first column of dg. Analogously, the second column of the matrix I'm trying to understand is the second column of dg. So, looks like a duck, quacks like a duck. This matrix is dg. Isn't that nice? Gotta love linear algebra. Powerful, powerful tool. Okay. So, we're kind of done here then. Remember, our goal was to find the factor that you multiply by the input area, du dv, to get the output area, dA. And we've found it. Here it is. This multiplicative factor, the thing you multiply by input area to get output area, is exactly what we claimed last time. It's the absolute value of the determinant of the derivative matrix. So, there you go. That's why that formula works. Everybody happy with that? Okay. Cool. All right. We've been exclusively in 2 dimensions so far. We're going to bump it up to 3 dimensions now. Good news, it's morally equivalent. It's kind of exactly the same. The big idea, change a variables function, this time from 3 in to 3 out instead of 2 in to 2 out. Right? But notice a very nice input domain turns into a very ugly, even uglier, really, output domain. Can you imagine having to slice and dice this solid here and not hit any corners? Forget it. It's not going to happen. You're going to hit tons of corners. And even worse, not only will you hit corners as you slice up the solid, but on each of those slices, which, of course, don't forget you have to slice up those slices. You're probably going to hit a lot of corners on each one of those, too. So this is a nightmare. You could have, I don't even know, but you could have dozens of integrals come up. This is a nightmare, logistically, right, as a domain. So being able to pull back in exactly the same way is massively useful. Again, the only thing you have to kind of keep track of is don't forget to include your stretching factor. Right? Don't forget that volume output is not the same as volume input. Here's our formula for our stretching factor. Again, we have this very convenient alternative notation for it, which I think is very handy. Again, it does some of your bookkeeping for you. It keeps track of whether you need to multiply or divide in the sense that, again, you get this bogus but awfully convenient memory tool, you might call it, that will always lead you the right direction. Right? So it's not a fraction. There is no cancellation, but if you pretend that there is, it'll always have you doing it the right way. And so it's really morally all the same. It's just 3-dimensional. This is going to be a 3 by 3 determinant that you'll have to deal with. That's a little annoying, but morally, structurally, same. Okay, so example. I got ahead of myself. For the purposes of this next example we're about to do, I want to point out a neat theorem. I made a reference to this on Friday, and that is that if you have a linear transformation represented by a matrix, the derivative of the transformation is the same matrix. It's weird. All right, a little bit unexpected. I'll say that it's unexpected. It feels kind of wrong. Doesn't it feel like it ought to? Should it be different? This bugged me for years until at some point I thought about what would the one-dimensional version of this look like. The one-dimensional version of this is if you have a function like this, then f prime is k. And it's really, therefore, pretty expected, right? I mean, that k, the derivative, same k. Not surprising at all if you think about it as, an extension of this, n equals 1 version of the statement. So anyway, I do think this is a healthy exercise. I encourage you to check this fact. Maybe just do it for 2x2s or 3x3s, but take it a notch up for at least from 1x1. Again, where it's trivial, just to see how this plays out. I think it's a nice exercise. Okay. As always, if you get in trouble, if you aren't sure how to do this or where to go from a certain point, come to my office hours. This is a very quick conversation. I'll be happy to straighten you out on it. No problem. Anytime. Okay, so with that in mind, here's our next example, our first 3-dimensional example. Let's suppose that we have a parallelepiped like this. Right? There's our parallelepiped. It's not even that weird of a 3-dimensional solid. And yet, if I want to use that as my domain for doing an integral, let's think for a moment about how horrifying. As, if I were to do this, slice and dice dx, dy, dz, or some, other rectangular, regular sort of, 5.4 kind of approach, I'm hitting lots of corners. And on each of my slices, I would be hitting multiple corners. You might not have thought through the geometry of this, but I think this is a horrifying fact to think about. Depending on how your parallelepiped is arranged, the cross section might have as many as 6 sides. A single cross section. So the whole thing is just unthinkably inconvenient. Okay, does everybody see the question here? All right, big trick on how to deal with parallelepipeds. Again, this is the hard-earned, brilliant idea that somebody came up with a long time ago, and we've all trickled down. Everybody's been benefiting from it since then. Here's the big idea: the vectors that define the parallelepiped, make those vectors the columns of a matrix, which then defines a linear transformation. And if you do that, then your parallelepiped is the image of the unit cube. And this is a pretty sweet pullback scenario. Right? I've got this horrifying nightmare of a domain on the right, but it is the image by way of a very convenient change of variables function. It is the image of the unit cube. My pullback domain then is the unit cube. And again, if you have to do a triple integral, it's hard to beat the unit cube for a domain. Everybody with me? So it's a neat trick. Now, you've got to think through for yourself that this is actually a true statement, that if you define your linear transformation in this way, the image of the unit cube really is this parallelepiped, and it's not that big of a deal to see it. After all, the images of the standard basis vectors are the columns of the corresponding matrix, but of course I arranged it to where those columns are the defining edge vectors of the parallelepiped. So, I mean, it just works. It just, boom. We rigged it up so that it would work exactly in this very convenient way. So, alrighty. And now, again, it's kind of all over. A couple of details to deal with, but we do the pullback, right? dx, dy, dz. Don't forget your stretching factor. How do I compute the stretching factor? Well, it's the determinant of the derivative matrix. The derivative matrix is the matrix for the linear transformation. That was our previous theorem. And so, you punch out that derivative, determinant. No big deal to compute that determinant. And then you're mostly there. Last little detail. What do we do with Z? How do I rewrite Z in terms of U, V, and W? Well, again, don't forget, when you're doing a pullback, right, the change of variables function is the formula for how you do your plugging in. X, Y, and Z are literally functions of U, V, and W as given by your change of variables function. And so, in fact, rewriting let's see here. This statement right here, what I have is X, Y, Z is my A matrix times U, V, W. And so you say you want to know what Z is. All right, here it is. There's Z. And so it must be this last row dot UVW. So I'll look at this last row for my coefficients. And therefore this Z is that right there. Everybody happy? So so we're all done. And we have turned our nightmare of an integral, possibly dozens, I don't even know how many separate iterated integrals I would have to break this up into in order to be able to do dx, dy, dz slicing. But now I've got it written as a pretty simple little formula. Integral UVW on the unit cube. It's one single integral. Massive victory. Massive simplification. Everybody see how awesome that was? Okay. Yes.
What made you choose Z?
That was given in the question. So the question was to compute the triple integral of Z. Yeah, that's all. Yeah. Okay. Alrighty. So moving along now. So that's all I'm going to say about what you might call the general change of variables. I have some specific applications of change of variables that we need to talk about now. And again, these are huge. These are well, anyway, certainly this coordinate systems business is a large part of the remainder of the section that we're in. Remember, this is a massive, massive section. We're not going to finish this today. Hope that we can finish this on Wednesday. We'll see, right? But anyway, so it turns out this is a very, very clever and powerful, but ultimately modest observation that recalling that we thought of coordinate systems themselves as being functions. Oh, how about we use them as change of variables functions? This is a real innocent little, hey, check it out. I have these things that are exactly of the appropriate dimension that they could be change of variables functions. And it's going to turn out that this is bonkers useful. Super duper useful. And for the moment, I'm going to try to restrain myself from using a certain choice of words that you will hear that I'll be using for the rest of the course, but I want to develop it a certain way. So for the moment, I'm just going to say we're talking about using these functions. Now here's polar coordinates, for example. We have easy formulas for x and y in terms of r and theta, standard formulas, right? Let's just use it as a change of variables function. Notice, as required, 2 variables in, 2 variables out. This is just straight up 2-dimensional change of variables. That's all. How about that? Isn't that convenient? Ditto, cylindrical coordinates. Old formulas. And we have literally 3 inputs, 3 outputs, and this is a change of variables function should I choose to view it as such, which I do. So, right, how about that? And then again, we have spherical coordinates too. Okay, well, here they are. X, Y, and Z as functions of rho, phi, and theta. 3 in, 3 out. This is a 3-dimensional change of variables function. So all we got to do now is compute the stretching factors. And remember, when you're computing stretching factors, you take the partials of the outputs with respect to the partials of, with respect to the inputs. And this is a little bit of algebra. Everybody should do this once in their lives. I've done mine. It's your turn. I think everyone should crank this out. It'll take you 30 seconds. No big deal. You take a few partials, you get a matrix, you take the determinant, and the answer is R. There's your Jacobian determinant. For cylindrical coordinates, well, there's a 3x3 matrix, right? So that's a little annoying. A little bit more algebra. It's not that bad. It'll take you 45 seconds. And the answer, weirdly, also R. How about that? Let's take a moment to recognize that these 2 stretching factors, polar and cylindrical, the stretching factors are the same. I call this more support for why it's advisable to think of cylindrical coordinates specifically as being 3-dimensional polar coordinates. Right? Because, they're really very much the same even in this calculation. Alrighty, and then things do get a little bit different with spherical coordinates. And again, everyone should do this once in their lives. And this one, this is going to take you 5 minutes. This is not a 30-second deal, but this is going to take you several minutes. But again, it's a healthy exercise. It's good mathematical weightlifting. Take the appropriate partials. You get a 3x3 matrix with a fair amount of trig in it. You take the determinant. Oh gosh, you got to write that thing all down. You multiply it out, and there's a bunch of terms that's going to go all the way across the page. But then you'll start to notice that Pythagorean identities kick in, and it simplifies massively. And it turns out that these spherical coordinates, Jacobian determinant, Rho squared sine phi. It simplifies really, really well. Everybody on board? So again, that's algebra. I'm going to let y'all, again, everyone should do it once in their lives. I did mine. It's your turn. Okay. All right. So here's the thing. Don't forget our stretching factor is always the absolute value of the Jacobian determinant. That absolute value matters. It's really important. If you don't put that absolute value in there, you will get wrong answers. And more to the point, your reasoning will be incorrect. It'll be importantly incorrect. So you've got to have that absolute value in there. Which is annoying. Nobody likes absolute values, right? I have to have a separate formula for what do I do when R is negative and what do I do when R is positive, and oh gosh, what an inconvenience. So here's the hack, the streamlining that most people choose to take advantage of, and I strongly urge you to take advantage of this as well. And that is to make the following choice. This is not a law. You don't have to do this. You should, for your own convenience. Should do this. Just make sure to choose when you're setting up how you're going to do business, when you're choosing among the many polar coordinates that you could choose from to define whatever whatever region you're looking at. Just choose polar coordinates where R is greater than or equal to 0. You always can. So do. Right? And if you think about it, if you make this choice, if you choose to have R being greater than or equal to 0, then you are taking the absolute value of something that is never negative, and then the absolute value is just itself, and now your stretching factor is just R. The absolute values go away. No problem. We don't have to deal with absolute values anymore. If you make this choice to always use non-negative values of R. Is everybody on board? Okay. All right. Same thing here. Right? Choose R greater than or equal to 0. It's the same stretching factor formula. I have the same motivation. I make the same choice. And again, the absolute values go away. Now here's where it does get a little bit confusing. What do I do in spherical coordinates? A lot of people incorrectly reason that, it was R that had to be positive for the previous two coordinate systems. And, spherical coordinates doesn't have an R. Yeah, okay, but rho is kinda, sorta like the R. And so maybe we should just choose that rho should be non-negative. That would seem like the analogous thing. And if you think about it, you look at this expression here, our Jacobian determinant, the thing on the inside of the absolute value. If I were merely to stipulate that rho must be positive, that doesn't change a thing. Rho was going to get squared anyway. Whether rho is positive or negative is a who cares issue. Right? And the fact that it kind of like the R doesn't matter. That's an absolute red herring. It's not at all relevant. What you need in order to make sure that the thing we have on the inside here is never negative, I need to figure out how I can arrange for sine phi to always be non-negative. And so you got to think about the trig of it all, right? And values of phi, and what values of phi can I choose that will make this work out? And the answer is, as long as phi is between 0 and pi. Now this is you got to think back to your trig days, right? These values of phi will ensure that sine phi is never negative, and of course it's perfectly obvious that rho squared is never negative. That's not an issue at all. And so then, boom, again, we have positive on the inside of our absolute values, and the absolute values go away. So this is the common misunderstanding. This has got nothing to do with rho. It's all about phi. Is everybody with me? Okay. So here's the best news of all. These values of phi, these are everybody's favorite values of phi anyway. Right? So promise that you will only do exactly what you wanted to do. And as a reward, you get to do another thing that you, of course, always wanted to do, namely throw away your absolute values. So it's win-win. But you gotta make the right choices. Okay. All right. So there we go. Let's dive in and do an example. Let's see here. So our domain here. Let's suppose I'm doing an integral on the first quadrant portion of the unit disk. So here's my domain. The integral in question over which this is, or for which this is the domain. I'm going to do an integral of x squared plus y squared, whatever, some expression. I'm going to do that integral, and I don't like this domain because, of course, it's got a curvy top. If I slice, whichever way I slice, one of my variables is going to be a square root expression of the other. I don't like square roots. Square roots get into my integrands eventually, and now I'm doing an integral that involves square roots, and nobody wants that. Right, so I'm going to call this an undesirable domain. So now we just have to think about, all right, in what sense is this an image of something else? And I claim that this quarter disk is an image of this rectangle, this much more desirable rectangle. Of course, think about how you're going to slice that up over here in the r theta plane. It's a rectangle. It's got constant bounds. We love that. Okay. All right. So now I'm making a claim that we do have to think through that this is in fact the correct pre-image. So let's kind of walk through it and see what happens here. Let's look at this edge right here. What's the image of this edge? And well, let's see. That edge is on theta equals 0, and r goes from 0 to 1. So as it turns out, that's that edge in the xy plane. Now let's think about this edge there. That edge is on r equals 1, where theta goes from 0 to pi over 2. So that's that edge right there. Is that cool so far? Everybody following? And then let's see here. What have I got here? What is that edge? That edge, theta is pi over 2, and r goes between 0 and 1. So, well, that's this edge. And then lastly, what can I say about this edge here? Well, that edge is entirely on the line r equals 0. The whole line r equals 0, I mean, any point that has r equals 0, it's in the xy plane is going to be the origin. Right? So with that in mind, I think it's a pretty easy pitch that this rectangle has as its image this quarter disk. How are we doing? Is everybody happy? All right. Okay, so cool. So now I just say the magic word, change of variables, right? And I get to then rewrite an integral on the xy domain as an integral in the uv domain. Let's see here, r and theta. This is easily sliced to get these bounds here. Let's think about that, step by step. Theta, range of values of theta on this domain. Theta slices look like this. I clearly start at 0. I clearly end at pi over 2. So my theta bounds are 0 to pi over 2. Then, let's see here. Looking at a fixed value of theta, let's now think about what's the range of values of r. Well, on that theta slice, r starts r starts at this point where r is clearly 0. R ends at this point where r is clearly 1. And so r goes from 0 to 1. Is everybody okay with that? All right. Okay, don't forget your stretching factor. Super easy to forget that. So easy. It's a big deal, too. If you think about it, the stretching factor is kind of the only thing here that isn't just kind of plugging in formulas, right? It is the only subtle, significant, It's the only multivariable calculus, thing in some sense that you wouldn't have just guessed. Right? So that's a really big deal, and it is so easy to forget. You can get easily distracted thinking about, what am I slicing, and slices of slices, and how's the algebra work, and accidentally forget to put in your stretching factor. Please, please, please don't let yourself forget that. It's a big deal. It's a lot of points. It has to be, because, again, everything else is kind of plugging in. So, anyway, please be careful. And then let's see, I got to rewrite x squared plus y squared, and now we got lucky on this one, and x squared plus y squared happens to be an easy formula in terms of r's and thetas. It's just r squared. So, look how easy the integral becomes. All together, my integrand is r cubed. The antiderivative of r cubed is 1/4 r to the 4th. You plug in your bounds, easy integral, boom, 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 and it's all over, and we have our value. Notice no square roots anywhere. Very nice. Is everybody happy? Okay. All right. Okay, so this is our first example of using polar coordinates as a change of variables function. Now I want to take a different point of view on this. I want to develop an idea, sort of a point of view is a pretty good way to say this. A point of view on this that is easier to visualize, that's easier to do the geometry, and that is to make observations that everything that happened in the r theta plane in this argument, everything that happens, you can see it in the xy plane. And if you can see all of the r theta action in the xy plane, I don't even really need to draw the r theta plane at all. That's the big idea. So my immediate observations here. Theta slices. Now keep in mind, theta slices are slices perpendicular to the theta axis, right? So we did this move here. These were our theta slices as we sliced up our pullback domain. Notice they're constant values of theta, and I know what that looks like over here in the xy plane. These are what it looks like when you take constant values of theta. Therefore, these are theta slices, and I can see them clear as day right here in the xy plane. It's nice. Likewise, r slices. If I wanted to draw r slices, well, slicing perpendicular to the r axis, there's my r axis. This is what r slices look like. Constant value of r. What does a constant value of r look like in the xy plane? Well, they're circles, bits of circles, like that. I can see it clear as day right here in the xy plane. So, with all of this in mind, I'm going to now do the exact same example that we just did up here. Exact same example. Except I'm going to do it now without drawing any of that. Everything that I need from over here, I'm going to observe instead over here. So here it is. So again, crossing this out. I leave it visible so that you can refer back to it if you want for convenience. But we're going to now do the whole problem over here on the right hand side. I say I'm going to do polar coordinates. Fine, polar coordinates. dx dy is r dr d theta. Okay. Stretching factor is the same. It doesn't matter what pictures you draw. Stretching factor is what it is. Let's see here. Likewise, x squared plus y squared, still r squared. Nothing changed there. Let's think about the slices. What is my range of values of theta? Well, my theta slices that I drew over here. No, don't. We don't need to think about that at all. Let's just draw the theta slices over here. And I can just immediately see this is my first slice. That's my first theta slice. It is immediately clear that's where theta equals 0. So lower bound for theta, 0. Everybody see what I'm talking about? Likewise, upper bound, last slice is that. That's straight vertical. That's where theta is pi over 2. So, boom. my upper bound for theta, pi over 2. Right there in the xy picture. I don't need to draw any of this over here at all. So this is again a different point of view on these kinds of integrals. We give this a name. We are in fact doing change of variables. Don't forget that there is a change of variables underneath it all. But without looking at that at all, looking just at this picture, right? It's just that we're using polar coordinates to understand the integral that's happening on this picture, and so we say we're doing the integral in polar coordinates. That's just slang, streamlined language describing I'm doing a change of variables where I'm using the polar coordinates conversion formulas as my change of variables function. That's a mouthful. It's easier to say I'm doing it in polar coordinates. Okay, good place to stop. We will pick up here on Wednesday. Y'all have a good day. See you later.